Saxon Algebra 1, Lesson 73. Look, students, we're starting week 20 of the year. Be proud of yourself. You're working so hard. Our lesson today is algebra, straight algebra, and it is related to this factoring we've been doing. We've been factoring trinomials. And a trinomial looks something like this, right? It's got the x squared and the x and the plane number, 3 parts, that's the tri. And we look at something like this and we go, okay, we know it's gonna be 2 binomials. We know we need to look for a pair of numbers that multiply to this and add to that. It's 2 and 1, and so then we can write in x plus 2, x plus 1. And that's our answer, right? We've been doing this. This kind of factoring we're going to do today, which is called the difference of 2 squares, is even faster and easier. Difference of 2 squares comes about when you notice a really strong pattern in, it's not a trinomial, but when you have an expression and you see this pattern, you know immediately how to factor it. Let's take this example first. X squared is a perfect square, right? It's x times x. And y squared is a perfect square. It's y times y, right? And in between the two is a minus sign. It's got to be a minus sign. You can't do this factoring if you don't have the minus sign, and the other thing you need, as I've said, are the perfect squares. X squared is the perfect square of x. Y squared is the perfect square of y. Now, it can get a little bit trickier. What if it's something like this? 4p squared minus 25. Okay, well, we notice that 4p squared, well, the perfect square of 2 is 4, and the perfect square of p is p squared, right? So we can look at this as the square, and we can find the square root of it, right? 25, oh, well, that's the perfect square of 5. And then once again, we have our essential minus sign. These are, what I'm pointing out is these are the indicators we look for to suggest we have a difference of 2 squares situation. I'll tell you how we factor them in just a minute. Here's another example. What if we had m squared minus 16? We go, oh, okay, well, the square root of m squared is m, which is another way of saying m is the perfect square, right? We can talk about it in circles. 4 times 4 is 16. And there is our lovely minus sign. So all 3 of these original expressions I showed you, notice they only have 2 parts, but they all work for difference of 2 squares. And we recognize, oh, look, square, square with a minus in between. Square, square with a minus in between. Square, square with a minus in between. That's what we're looking for. That's when we know that we can use the difference of 2 squares theorem. And that looks like this. Oh, let me just write this. I'm going to write this again. I know I wrote it up there. Difference of 2 squares is what we call this factoring strategy. Remember that the difference, the word difference, is because we have to have a minus sign in the middle, and 2 squares means that both values are perfect squares. They can be letters or numbers, as we saw in this example. When we recognize that we have both of these conditions, we can factor it in a snap. We don't even have to think about numbers like this. We simply know that if we've got perfect square minus perfect square, we can factor that as And we're going to do some examples so you'll see. We can factor it like this, okay? Automatically. We find the root of it, we find the root of it, and then we just copy it out like this. We kind of jump right to the art project, right? We don't even have to think this hard about it. This is what we're learning today that's new and different. We're learning this new way to factor that as soon as we recognize that we have the minus sign and the two squares, we can just jump right into it. One thing I want to point out to you is that we're multiplying these two quantities. Sometimes I write the plus first, sometimes I write the minus first. As long as you have one of each, it doesn't matter which goes first. All right, I'm going to recopy this to the top of the next page because we're going to use it to work some problems. A squared, you need to memorize this. Oh, that's equals. All right, example 73.1. All right, first John throws us a little curveball. I look at this and I go, okay, 4 is a perfect square, x squared is a perfect square, right? It's x times x. But I don't have a minus sign in the middle. My minus sign's over here, which I don't like, and the whole thing feels off. But then I go, oh wait, I can rearrange it. Now it's perfect. If I think of this as being the a squared and this as being the b squared, I can write over here, a equals the square root of that, which would be x, right? And b equals the square root of that, which would be 2. And now I can write my answer, x minus 2, x plus 2. Once I identify the square root of each side, I can use those to just fill in the blanks. This is my final answer. Again, we can put the plus binomial first and the minus one second. It doesn't matter. Let's do another, because I'm having so much fun. All right. 49m squared minus a squared. Okay, I like that the minus sign's in the middle. This is a square, this is a square. We have to find what are the square roots of those numbers. So I remember this is like the a squared minus the b squared, right? So in this case, our a value is the root of this. Okay, the square root of 49 is 7. The square root of m squared is m. So this would be 7m. And then b, well, this is weird because it's a. That just feels weird, doesn't it? So then we can write our answer just using this factoring pattern. Right? The only thinking we have to do is to calculate our a and b values. Then we just art project. 7m plus a. Oh, I switched the order, didn't I? Doesn't matter which order you put the plus and the minus as long as you have one binomial of each. Example 73.3. There are 4 of these in all. 73.3 is minus 36 a squared plus 25. Okay, we look at this one and we see again, this minus sign is in the wrong place. I don't like that. So what we can do is just rearrange it. Nothing fancy, there's no equal sign. We're not swimming any fish. We're just changing the order that we write the problem. That's perfectly fine to do. The numbers are perfect squares. We've got a y squared and a squared. It's perfect. I remember this I'm calling my a squared and this I'm calling my b squared in order to fit this formula. So I write a equals, let's see, it'd be 5y, and b equals 6a. This a has nothing to do with that a. It gets a little confusing, but that's why I write the letters underneath so that we can compare our formula to our problem. Okay, 5y minus 6a, 5a plus 5y, sorry, plus 6a. Yay! I did the binomial with the minus sign first. I'm just mixing it up. All right, and then let's do one more of these, and then we shall switch topics. This is 73.4. And this one looks a little messy, doesn't it? Oof. I like the 36, I like the 49. That's 6 squared, that's 7 squared. That's fine. I feel good about that. I don't like where the minus sign is, so I'm gonna have to rewrite this. And again, this is not swimming fish. There's no equal sign here. We're just rewriting it. And again, if I was doing this as a student in my homework, I wouldn't write down the wrong way. I would copy it the right way. Okay, so let me write down our pattern again. A squared minus b squared can be factored as quantity a minus b times quantity a plus b. All right? That's our tool. That's our difference of two squares factoring pattern that we can use. So now I have to figure out what the a and the b are. This I'm calling a squared, this I'm calling b squared. So over here I'm gonna write a, and I'm gonna write here, just like we have been doing, I'm writing the value, numbers and letters, that are the square root of this number. Okay, the square root of the 49 is 7. The square root of the a squared is a. That one's pretty easy. This one's the crazy one. B equals. Okay, let's figure this out. Square root of 36 is 6. Got it. Now we have 6 x's rather, right? 1, 2, 3, 4, 5, 6. So what we can do is divide them in half, right? Because if this is x to the third and we square that to get this number back, we would we would multiply, right? Because it would be this x to the third, and then we would be squaring it to get this value. 2 times 3 is 6. Good, it worked. All right, so if you're confused about how to take the square root of the exponents, write them out and divide it into 2 groups. And that will give you exactly what you need over here. Same thing with the y's. 1, 2, 3, 4. If you're all confused, write them out and divide them in half. This would be y squared. And now we can write the factor of this. We can factor this expression as 7a minus 6x cubed y squared, 7a plus. Okay, so when these exponents get crazy, if you're confused at all, write out the number of the base, right? Write it out however many times the exponent tells you. Divide it in half. That's the number that goes over here, right? Here we had 3 and 3. Here we had 2 and 2. That's how I got that 3 and that 2. All right, and then this is our final answer. Yay. All right, this is the difference of two squares theorem. It's very, very handy because, like I said, once you recognize that you have, go back to the beginning. Once you recognize that you have the right setup, both values are perfect squares and you have a minus sign in the middle, you can factor this without even calculating anything, right? You just have to figure out what's the root of the a squared, root of the b squared, right? So you have these numbers to plug in. That's the only hard part about it. Otherwise, you're just filling things in. All right, that's the first part of this lesson. Let's switch gears and talk about probability. And this is called probability without, emphasis on without, replacement. And I'll give you a great example. Let's talk about our good old urns, right? The urn is a special sort of container that we can use to put things in. Okay, and so in our urn, it's got 3 black marbles, 1, 2, 3, and 5 white marbles. Pretend that's black and white. It's orange and clear. A marble is drawn at random and replaced. Then a second marble is randomly drawn. Okay, the first question, so we've got 3 black and we've got 5 white. And that's a total of 8 marbles, right? Now, the first question is, what is the probability that we draw a marble and then we draw a second marble that both marbles are black? And in this example, we're putting the first marble back. So we say that's with replacement. Okay, so let's see. There are 3 black out of 8 in all. Remember, the probability of something happening is the number of desired outcomes over the number of total outcomes. So in this case, we want to get, on the first one, we want to get one of these blacks. So that would be 3 out of 8. And then we take a second turn, and again, our odds are 3 out of 8. And so the odds of drawing a black one and then drawing another black one are 9 out of 64. And that's assuming that that first marble that we drew, we put it back into the urn. Now, let's change this scenario just a little bit. In this case, we want to know what happens if we draw a marble, it's black. We don't put it back in the urn. Okay, so in this scenario, we take out one of the black ones and we set it down here on the tabletop after our first turn, right? That is called without replacement. So now we want to know the probability of getting 2 blacks in a row without putting the first one back. So what we see is that on our first go, it would be just like this, right? We'd have 3 blacks and a total of 8, so it would be 3 out of 8. But after that first turn, we would put the first black one we chose down here on the table, and now we would be finding what's the probability of getting a second black. Well, it's different because now we only have 2 blacks left in the urn, and we only have a total of 7. If you don't replace the items that you draw out, the probabilities change as you go. And so, 6 out of 56, and we can divide both of those numbers by 2. 3 out of, what would that be, 28, right? So, replacing or not replacing the items that we're selecting will change the probability of getting more of them, right? Which makes sense. If we take one of the good ones out and put it on the table, then that limits the number that we have to choose from the next time. Okay, let's try another one of these without drawing quite so many pictures. This was 73.5. And then let's do 73.6 over here, and we will be done. Okay, this time, the marbles in the urn are the classic example of this. An urn contains 4 red marbles and 7 blue marbles. I don't have to draw the picture if I don't want to, but I do need to write it down, and I also need to do this. That means there's 11 in all, right? Because remember, probability equals the number of desired outcomes over the number of total outcomes. And if I'm choosing marbles, then the desired outcomes has to do with the color I want, and the number of total outcomes means how many marbles in all. Okay, so I want to know, let's see what John asks us. What's the probability of drawing the first red and the second blue? Okay, so that's red and blue. If the marbles are drawn A with replacement, and then part B, we want to know the same thing, the probability of drawing a red and then a blue without replacement. This is the way John loves to set these up. He has us calculate the probability with replacement and then without. So here's our data. These are the marbles in our urn. We know that the probability of drawing a red would be 4 out of 11, right? Because there's 4 reds out of 11 marbles in all. That would be the first one. And then the second time, we're putting it back, so it would be the same the second time. 4 out of 11. Oh, no, not the same, because this time we want to draw a blue, not a red. So that would be 7, right? The first time we want to draw a red, 4 out of 11. The second time we want to draw a blue, 7 out of 11. So our final answer would be 28 out of 121. That's a big number. It's correct though. Okay, now let's see what happens if we do it without replacement. I'll put my numbers down here a little bit. The first time we want a red, there are 4 out of 11. That's the same. But now we've taken one of those red marbles and we've put it outside the urn. So then it changes to, we would only have 3 red and 7 blue for 10 total. This is the reality we'd be using for our second choice. So that would be 7 out of 10. Probability of drawing a blue after we've drawn a red would be 7 out of 10. Not 11 because we took one of the reds out. This one's a little more confusing than the first one because we drew a red the first time. So that one is gone, it's sitting on the table. We still have the 7 blue, but now there are only 10 marbles in the urn. So this is what we've got. If you would like, you can cancel before you multiply. That's perfectly fine. Let's do that this time. 2 and 5, so that gives us 14 out of 55. And that's the correct answer here. Okay, so remember that when you're not replacing the items, you have to think carefully about what you've got on in your urn the second time because you changed it. The first time you don't change it, you just put everything back. In order to compare these two probabilities, in order to make much sense of this problem, we would have to make them have a matching denominator. This is a calculation that comes up a lot in standardized tests. We can't compare numbers if they don't have matching denominators. So we would either have to make their denominators match, or the other thing we could do is change them both into decimal numbers. But remember that we can't compare those numbers at all because their denominators are so different. All right? That's the end of lesson 73. I hope you enjoyed it, and I hope you have fun with your homework. Thanks, bye.